Добрый день, уважаемые коллеги! Вас на нашем втором вебинаре, посвященному седиментационному моделированию в DionisosFlow. Для начала я хотела бы представить нашего лектора. Это Самир Боу-Дахар. И, соответственно, модераторами сегодня будет являться Алсит Тибо и я, Ольга Емельяненко. Если в течение нашего семинара у вас возникнут какие-либо вопросы, то вы можете их писать во вкладочке Questions, которая у вас появилась в правой части панели. Соответственно, вопросы пишите на русском, на английском, как вам удобно. Также есть вкладочка Polls, где я буду писать какие-то вопросы, которые для оценки качества. Если вас не затруднит, пожалуйста, ответьте также на них. Во время семинара будет выключен полностью звук. Соответственно, все вопросы, которые, например, останутся неотвеченными, к примеру, если мы вдруг не успеем на них ответить, мы обязательно на них ответим в течение ближайшего времени. Также, если вдруг у вас останутся какие-либо вопросы, которые вы хотели бы обсудить, я не знаю, по телефону или, может быть, в более обширной форме, вы можете всегда с нами связаться по почте info.moscow@bsip.com. Ну и, естественно, всегда можете приехать к нам в офис в Москве, который находится на Вавилова, для того, чтобы мы обсудили все вопросы, которые вас интересуют. Надеюсь, данный вебинар для вас будет очень полезен, поэтому можем перейти к началу. Окей, Samir, thank you.
Thank you, Olga. So hello and welcome everyone to BSIP Labs software webinar number 2 on DionisosFlow for forward stratigraphic modeling. Today we have prepared for you a bunch of topics, a collection of a little bit different applications and topics in DionisosFlow that we divide into 4 parts of the agenda. First, we will introduce you to DionisosFlow and the concepts of forward stratigraphic modeling. Then we will we selected a few case studies with various environments and various scales that we will present to you, followed by a short question and answer break. Then we have some slides about the DionisosFlow organic matter tool, so where we can model marine and terrestrial organic matter. We'll present that tool briefly to you, and followed by a small case study and a question and answer break. Then we have a few slides at the end about the integration of DionisosFlow models with reservoir characterization. So how to take those models further and really make the most use out of them at the reservoir scale. And then a Q&A session, and we finish the webinar. So let's start with the concepts and objectives of forward stratigraphic modeling with DionisosFlow. But first a little bit about the history of this software. So DionisosFlow is our forward stratigraphic modeling solution. The research into that has started, the R&D started in the mid-90s with several industry players involved in this research that eventually led to the industrial version of the software in the early 2000s, and that was Dionisos, the standalone version. In about the years 2013-14, Dionisos became integrated on our OpenFlow platform together with other exploration and production software, and it became called DionisosFlow. And what's very interesting to point out here is that DionisosFlow is a continuously evolving tool where there's new capabilities being added all the time, thanks to the research that is always ongoing with EFP and funded by major industry players. An example of such an addition was the latest organic matter deposition tool that was the result of several years of joint industry research. And of course, the research that is done is guided by the needs of the industry and the needs of clients. Now, the fields of application of this methodology, they range from all the way from frontier basins into field scale. And the important thing to notice here is that the objectives of application of this methodology, they change together with the scale of application and the nature of basin we're working with. So if we're in a frontier basin, for example, then of course the questions that we would like to answer are related to the reservoir presence and distribution and extension. Same for the seal and the source rock presence, distribution, quality, and quantity. While when we go into mature basin, then the questions are the different related to identification of subtle stratigraphic traps, for example. And when we go into a field scale, then we have the objectives such as an improved history matching, or to tackle some production mitigation issues. In terms of environments, we are able to apply it in siliciclastic environments, carbonate environments, or mixed systems together with organic matter as well, with the various lateral and vertical resolution. Now, the objectives of applying for stratigraphic modeling vary with different scales, but the added value is very similar. So when you go into petroleum system models, you would get detailed, so when you're working on basin scale and then your result will be eventually injected into petroleum system models, you would have much better stratigraphy, facies models, and geometries that will get into your petroleum system model in terms of net to gross maps of your reservoir, net thickness of your reservoir, thickness of your seal, your source rock, your TOC, and facies maps. But also when you're working on a reservoir scale, you also will have much more detailed stratigraphy, and so you to analyze the connectivity of your reservoir, detailed facies maps, and very importantly, detailed geometries and depositional geometries, realistic depositional geometries that you could then transfer into your reservoir model, which we will see a little bit later, some slides on options to do that and workflows to do that. Now let's go a little bit into some of the concepts for forward stratigraphic modeling. As the name suggests, it's a forward approach where you start at a certain point in time and you simulate the filling of a sedimentary basin through time, or an interval within a sedimentary basin, while at different points in time you have to account for some parameters, or to have a proxy for some parameters. For example, the accommodation space. So you have to tell the software how much space do you have to fill, how much volume. Then once you have that kind of a proxy for that information, or an estimate, you can bring the sediments in, and the sediments can be brought from outside in form of clastic sediments that will that come from weathering and erosion of the hinterland, or in situ production, so production of sediments within the water column in form of carbonates and different types of carbonates that can be controlled by different ecological factors and produced in different parts of the basin. And the third type of sediment is the organic matter, which can be marine, produced in the water column in the photic zone, or terrestrial, brought with the clastic sources as a terrestrial organic matter particle. Now, once we have the sediments in, we need to move them around. We need to transport sediments. And the way we transport sediments in DionisosFlow is using our diffusion equation, which mimics the macro scale sediment transport very well. And it mimics the processes such as slope failure and turbidise, fluvial and deltaic processes, and other coastal processes that result in movement of sediments. Of course, this workflow is then calibrated. The obvious calibration data is well data, geophysical well data, or core data, and seismic data. But also it is possible to use outcrop data if that's present, or even present-day analogs to compare geometries of and scale of bodies that we would produce or reproduce using DionisosFlow. Now, to get a little bit into the clastic concepts, to give you a little bit more insights into how do we model clastics. It's very important in clastic systems to know where's the source. So here's an example of a delta, for example, where you see that we have to know where are the sediments coming from. So the magnitude as well of that sediment source and the type of sediments that might come in, and the scale of the sink, of the accommodation space. So in Dionisos, we start by an estimate of that accommodation space by subsidence maps plus sea level variation through time. Then on it, we add the sediment input locations and the magnitude of water discharge that's coming in. the different proportions of sediments that are coming in, how much sand, how much silt, how much clay, and so on. Then we add to that the time steps, which usually comes from the biostratigraphy, and then we're good to go to run a simulation and assess our system. So here you see a submarine channel and submarine fan system evolving through time and being affected very much by salt movement. And the scales that we could get to, the resolution we could get to in terms of vertical resolution is centimeters to kilometers, depending on the scale we're working with, whether it's a reservoir scale or basin scale, and laterally as well from tens to hundreds of kilometers. The sediment movement is calculated by our diffusion equation, which works on the macro scale, very well transports the sediments by mimicking gravity, transport, water transport, and wave action. For the carbonate systems, the story is a little bit different. The carbonates add a complication of biology, add the complication of ecosystems. So we have to account for that. So the way we do it is by having a production reference, and then adding to that some controls such as bathymetric controls, wave influence, ecology influence. So different types of carbonate grow in different environments. For example, if I want to grow, if I have some reef carbonates, then I need to have in those conditions that my reef carbonate would grow at shallow waters and at high wave energy, while my lagoon will grow at also shallow waters, but at weak wave energy. So I can specify different ecologies, different wave energies, different bathymetries to grow different types of carbonates. The interesting thing about the carbonates, though, is that the knowledge is, the knowledge is transferable. So if I model a carbonate system in the lower Cretaceous in somewhere in the Tethys at tropical environment, I could take almost those identical values and use them in a similar environment, but in Mexico or like somewhere in very in the other side of the world, but similar environment and similar age. So the knowledge is very much transferable with the carbonate systems. An example of how the model behaves in, or how we can account for mixed systems. So here to the left, you see a model running that is just a carbonate model, a carbonate ramp with shoal complexes growing here in yellow and prograding in several directions towards the outer ramp, the mid ramp and the outer ramp setting, and topped by subca environments, topped by salt. To the right, you see the same exact model, but we have added two clastic sources to it where the arrows are. So here you see now the start of the growth of some of the shoal complexes in yellow, but you'll notice that the progradation of shoal complexes, for example, here towards those clastic sources is hindered by the presence of turbidity in the water. So there you see the interaction of both systems, the carbonate system and the clastic system, and how one can hinder the other one from growing in a mixed model. And the third type of sediment that we model is the organic sediment, is the organic matter. And we have the ability here to model different systems. So in terms of primary productivity, you have primary productivity that is controlled by upwelling or by riverine sources. We can, in our editor, to account for both separately or working at the same time. We also have the possibility to bring in organic matter, terrestrial organic matter. And in terms of preservation configurations, we can mimic different kind of preservation configurations that could change also through time. So you could have a restricted basin going into an open marine basin, into a restricted basin again. So you can change that through time while modeling during the interval that you're modeling. A restricted basin, for example, is like the Black Sea, and an open marine with oxygen minimum zone is an example of that would be the present day offshore Peru or offshore Namibia. And of course, it's very important to account for vertical and lateral transport for the organic matter for vertical transport and to calculate the flux of organic carbon to the seafloor, we use Martin's law. And for the lateral transport, we use the diffusion equation similar to all other sediments in the system. The kind of results that you get from DionisosFlow is quite a big range, but to summarize it all in one slide, you'd have a 4-dimensional block that will give you information on your petroleum system elements, so source rock, reservoir, and seal, and that is quality, thickness, distribution for the reservoir, net to gross, connectivity, facies, and thickness, but also it gives you information on the depositional environment, so paleobathymetries, wave energy, water discharge, and of course that 4-dimensional block, facies block that you will get can be transferred with just a few clicks, can be transformed into a synthetic seismic that you could then compare to your original seismic data. Now let's go into a real-life example from an extensive exploration at basin scale case study from Newfoundland. So that is the Orphan Basin. And so we went to the Orphan Basin with the following objectives: to basically identify the main place and petroleum system components, so reservoir, source rock, seals, and traps, to also understand the evolution of the hydrocarbons through the system, so the oil and gas generation and charge into reservoirs and traps, in order to unrisk the resources in place and reduce the exploration risks. The workflow that we have adapted is our usual workflow for frontier basins. So we start with the traditional sedimentology and stratigraphy and well log analysis and seismic and structural analysis. That results into some synthesis in terms of GDE maps, for example, that will all go into starting a DionisosFlow model that will model the petroleum system, the whole interval, and delineate the different petroleum system elements. So again, the source rock, reservoir, and seal distribution. That will go into DionisosFlow, our petroleum system modeling solution, and then eventually into a thorough and comprehensive resource assessment. So we started with a relatively limited data set, which is usually the case for a frontier basin exploration. And we managed to pick a bunch of seismic horizons that, with the help of some well data, we interpreted and constructed a bunch of GDE maps for every one of those intervals. And from those, of course, there has been some conceptual depositional models that were generated that could tell us a lot about, would help us start building our Dionisos model by helping us select where we would put our sediment entry points, where we might have some carbonate platforms. So they do act as a starting point for the Dionisos model. But the Dionisos model comes in to fill the gaps basically between those horizons. So here we have only 8 horizons, but the Dionisos model would then fill in this gap with in a process-based approach to give us a continuous 4-dimensional block that has all the lithology information. So we go from conceptual GDE maps into a numerical 4D grid that gives the lithology information and again the depositional environment and in other environmental parameters in the model. That all goes into then a high resolution stratigraphic geocube that is very well calibrated and gives us through time the evolution of this basin and a much better resolution of the facies heterogeneities. So we have now the 3 components of the petroleum system. There's 3 elements of petroleum system modeled and calibrated in this process-based forward stratigraphic model. Then we can move into the risk analysis part. Here you see an example that is done for the reservoir. So you get to really dissect and your model and look at different qualities of your reservoir and map those areas with different qualities, produce a CRS map for the reservoir, so common risk segment map, for the reservoir presence, delineating the areas where you have high risk, medium, and low risk. You can do the same then from this model for your source rock and your seal. Stack all of it together, you'll have a cumulative CRS map for the three from DionisosFlow. Add to that information the maturity modeling and the charge from petroleum system modeling into DionisosFlow. And then you'll get your cumulative or your combined CRS map that delineates to you your leads and the areas where you have low risk for exploration. So that was an example from large-scale exploration where we do not have much data and we need to reduce the risks. Now we will move into a completely different part of the world and different environment and different even mentality or objectives of using this methodology. So we go into a giant carbonate field in the Middle East. So here we have a carbonate reservoir that has been deposited on a gently dipping ramp along the Arabian Plate, where we generally had a stable tectonic setting, but we had some development of first a gradational platform. Then we start having some clinoforms and progradation of rudist, which shows forming clinoforms that have some bottom sets rich in mud and wax stone, and resulting in a fairly heterogeneous reservoir. And the challenge there was that we had a discrepancy between the reservoir's behavior and the reservoir models that were present by then. So the reservoir's behavior did not match the models that we had. And the objective there was to produce a reservoir model that has a much better resolution of the heterogeneities that are present in the system. So we went into this process-based approach and we started building a Dionisos model. And an important difference between this case study and the previous one is not only the depositional environment, that this is carbonate and the previous one was a mixed environment, but this one has much more calibration data. We have here more than 45 wells that we calibrated to, plus we have excellent seismic stratigraphy. So the controls on our model were plenty. So we started by building this field scale model with an algal mound that is a grading that gradually moves into progradational and then topped by on-lapping basinal infill. And to make use of the luxury of having a lot of data in this field, we decided to divide some of this core and well data into two parts and use one part to start building the model and the other part to do blind tests to validate or to really put this methodology and this approach to the test and see whether it works or not. So here we'll show you an example of calibration of one of the sequences. So that's the sequence delineated in yellow over here. And here you see calibration example to 5 of the wells that we were using at the beginning. And here to the left, you see the well data, and to the right, you see the DionisosFlow results. Same for every one of those wells. And you see that we match in terms of texture very well. That's the colors match fairly well. And the thickness as well. So we match both characteristics. We need to reproduce the thickness that is present today, and we need to reproduce the lithology that is present today. And we do that very well here. We compare visually, but we can also compare numerically, so we can have some quantitative calibration indicators here for thickness and for the texture. And it's important to note here that this is a process-based approach. That means you would never have 100% match. It's very unrealistic to have 100% match in a process-based approach, unlike data-bound approaches where it's usual to have a very high match percentage. So an 80% calibration is a very good value for calibration of those kind of models. Now we go into the blind test. So we run the calibration test on the wells that we have not used, we have not touched during the building of this model, and we see that we are still very well calibrated, even in such a heterogeneous field such as this one. Now we combine both and we have still a very good calibration indicator. So we are confident with our model, we are happy with our model, then we can move it into the reservoir modeling workflow and perform flow simulations. Now, it's important here to note that it's not only the lithology that were transferred, but it's very important to transfer the geometries as well, as we have done in this case, and move those clinoforms into the reservoir model as well. We will see a little bit later some slides on how to integrate the Dionysos model and make use of it on the reservoir scale in order to perform flow simulations, reservoir model and reservoir models. So we will get back to this topic at the end of this webinar. But for now, I think we can have our first Q&A break. So Olga, I think the floor is yours now.
Not now. Now we don't have the questions. Уважаемые коллеги, если у вас есть вопросы, не стесняйтесь, можете писать их в течение, в принципе, рассказа нашего лектора. И сейчас, на данный момент, также можете все свои вопросы озвучить.
So, Olga?
No.
Should I continue?
Maybe during the next part we have any questions. Okay. Okay.
I'll go on then to the DionisosFlow organic matter module capabilities. Again, this is a tool that was the result of a few years of research, joint industry research between EFP and several industry players such as Total, Repsol, and Chevron, among others. This tool is currently fully integrated with the DionisosFlow workflow. It's a streamlined and versatile tool that allows for the user to input parameters that will allow them to model different organic matter systems, such as an upwelling or a riverine system, but also terrestrial organic matter, as we talked earlier, also different preservation configurations, and most importantly, a wide range of output parameters that you can calibrate to your observations, to your geochemical data, such as TOC, hydrogen indices, thicknesses, and other indirect proxies. So in terms of organic matter production, so primary production, the primary production of organic matter, marine organic matter, happens in the photic zone, and it is controlled by nutrient supply. And the nutrient supply can come by either upwelling of currents from the deep sea, or weathering and erosion of nutrients from the hinterland into the sea. And we are able in DionisosFlow to account for both separately or at the same time. To account for an upwelling system, you have to select this option where you have primary production, a value that is user defined, and this primary production will happen in the photic zone above a water depth that is specified here, meaning that above a depth here of about 200 meters, plus or minus 100, the upwelling current will reach the surface and induce primary productivity in the photic zone. For the riverine nutrient source, the situation is a little bit easier, where you have primary productivity highest at closest to the shore. So at distance to the shore that is 0, we have a user-defined value that is here 200, and that value decreases linearly to another user-defined value away from the shore here at a distance of 50 kilometers, but this also can be change depending on the user entry. To illustrate this better for you, we have this schematic here that shows for an upwelling system, for example. Let's say this is the 200-meter bathymetry, this is 100 and 300. That upwelling current coming from the deep sea will reach the surface, will reach the surface waters and the mixed layer and photic zone, where the primary production will happen above that bathymetry. So in that area, you will have that primary productivity that the user have entered. In the riverine system, nutrient source, you will have primary production that is highest near to the coast and decreases linearly depending on the user-defined numbers. To show you what is the effect that this different type of primary productivity has on the distribution of the source rock, we have here those two synthetic models that are very simple models just to illustrate the effect of those two different systems. So here you have the system of decreasing primary productivity from the coastline from here towards the offshore. And here you see that the distribution of the source rock is more widespread across this synthetic shelf and slope. And it disappears in the offshore where we have an open marine system and a lot of oxygen being replenished here. While to the left, we have an upwelling system that results into a band of source rock enrichment that is our oxygen minimum zone, where the source rock preservation is best, but above it, we have no source rock, and below it, we have no source rock. This is similar to, again, upwelling systems offshore Namibia or offshore Peru. Now, in terms of preservation configurations, also we have, as I said, we have the ability to model open marine or restricted basins. So for the open marine, we have still the same model that we had to the right in the previous slide, but here you see the oxygen configurations the configuration that we had for it. So we have the mixed layer in the photic zone, below which we start consuming the oxygen in the water. That will keep on decreasing until it reaches a certain bathymetry where the bottom sea currents will replenish this oxygen and bring us back into higher values of seafloor oxygen. And that is the effect of that is what we see here. So we see that at deeper waters, we lose the source rock because we have some replenishment of the seafloor oxygen with bottom currents. Now, to the left, we have the complete other end member where we have a fully restricted basin. Here we have the photic zone and the mixed layer, and below it we start consuming this seafloor oxygen, and we reach a point where we consumed everything and we do not replenish any oxygen in the sea, in the deep waters. So we killed any bottom currents here, so we have no replenishment of the seafloor oxygen. And the result of a very similar model, so both are models where the nutrients are coming by are decreasing with distance to shore, so both have the same primary production but different oxygen model, different preservation configuration. And here you see that the TOC distribution is very different from this open marine system here. You have still a lot of TOC in the deepest part of the basin, but you also have this band of enriched TOC that is basically the result of having both primary production in the water in the photic zone and preservation and oxygen at the seafloor being ideal for the source rock preservation. So both are really good for source rock preservation, resulting in very high TOC over here. If you go above that band into this zone here, this is a source rock that has been deposited due to high level of primary productivity, but the preservation here is not as good. While if we go down to this part of the basin, we have similar amount of TOC, but the controlling factor on the deposition of this source rock is different. Here we have better preservation, but not so good primary productivity, while here we have really good primary productivity, but not as good preservation. So here you see the different dynamics of where you are in the basin. Different factors control the source rock deposition. The output, the kind of output you get out of this tool is quite variable, but it's a useful list of parameters that include the sediment proportions, so the proportions of the different type of organic matter. Here, so far, we talked only about marine organic matter. We skipped the terrestrial for time reasons, but we have also the ability to account for terrestrial organic matter. So here you have, as an output, you have the sediment proportions of the different type of organic matter, but you also have the TOC weight percentage calculated for each type of organic matter and their respective hydrogen indices, also per bulk and per type of organic matter, together with several different kind of outputs that you can calibrate to your observed data. That could be thickness of source rock from wells, TOC, and hydrogen index. But very interestingly, you could calibrate indirectly to some of your of detailed geochemical data. So, for example, if you have some redox sensitive geochemical proxies, such as some biomarker data like pristine phytane, for example, you could calibrate that to our oxygen concentration proxy that is an output, is an automatic output when you're calculating the organic matter distribution. Of course, the ultimate goal is to understand the distribution of our source rocks and the corrosion quality that will eventually get integrated into petroleum system models and provide a much better assessment of hydrocarbon generation and quantities generated as well. Now we will go into an application of this tool in the Carson Basin. So a real-life example where we have modeled source rock distribution in a frontier basin, that is the Carson Basin offshore Canada. Again, similar to the Orphan Basin, this was an exploration scale study where we had to assess the reservoir, source rock, and seal presence, and model the production of, model the generation of hydrocarbons and the charge into reservoirs and traps to de-risk exploration. The workflow that we have used is very similar, so you're already familiar with that workflow that includes different scales, different disciplines that all get into DionisosFlow, then into TEMIS, then into and result into a thorough resource assessment. But let's focus now again on the source rock model. So as is recommended for forward stratigraphic modeling in general, it's good to start with a conceptual model that you would like to test or to analyze. The conceptual model that we have started with here is as follows. So we first went into paleogeographic maps and looked at the paleogeographic setting of our basin. And we noticed there are two very important things that can affect our organic matter deposition. And these two things are that, one, the paleolatitude of this basin, of the Carson Basin, from the Jurassic to the Middle Cretaceous, and the paleogeography was most probably not prone to upwelling. So this setting is not a setting that usually results in an upwelling system. So we have decided to go for the first option of primary production versus distance to shore. The second thing that we have noticed by looking at paleogeographic maps is that during the Upper Jurassic and the Lower Cretaceous time of our basin's evolution, we had a restricted basin, while in the Middle Cretaceous onwards, we started having an open marine setting. So we translated that into our preservation configuration, and that looks as follows. Again, we have the mixed layer and the photic zone over here, and from the bottom of that mixed layer, you start consuming the oxygen, and you see here that we barely have any replenishment of the bottom of the seafloor oxygen. So we have a very faint bottom current that we left that brings a little bit of oxygen into the seafloor at deep bathymetries. But if you go into the middle Cretaceous, so this setting here was the upper Jurassic, lower Cretaceous, while this setting here was adapted for the middle Cretaceous. So here we have, again, a decrease in the oxygen from the bottom of the mixed layer, and then it gets replenished again in deep waters due to this strong bottom current that we mimic, that brings in oxygen to the bottom waters. So we went with this conceptual model, and then of course, as we've seen earlier, these models are calibrated. For the organic matter modeling, we calibrate directly to TOC or to hydrogen index. Here's an example of calibration to TOC data. So to the left, you have your well data from this well in TOC weight percentage, measured TOC weight percentage. And here's your modeled, to the right, your modeled TOC weight percentage. Note that for the deep part here, we do not have any data, but we still have some TOC in the model. But again, it's also very important to mention here that we never match 100% to calibration data, but we match to trends and to about 80%, especially in modeling organic matter, because this is a very complex system that we're trying to model. So what we want to match is the trends, is the general behavior of the source rock, and we do match that very well in this example, in this borehole here. We have the first 2 cycles here of enrichment of TOC, then we have another peak over here in the Aptian. So here you see that we have restricted system all the way to this peak, and then from this peak onwards we have an open marine setting that results in this quick drop in TOC right after this peak over here. Now, to summarize what we got out in terms of source rock modeling from this Carson Basin, we have managed to identify 3 main source rocks. And here's an example of output that we have generated out of each one of those source rocks. What's interesting to notice here is the oxygen versus bathymetry situation. Here you see that for the source rock, which was an open marine system by then, we see that the lowest oxygen or the most anoxic conditions were not in the deepest part of the basin, but rather at an intermediate bathymetry. And going deeper into the deep basin, we have a replenishment of the oxygen. We move back into more like a dysoxic condition, or even slightly oxic condition. But if we go to the source rock, the situation is very different. Here you go, if you look at the bathymetry and the oxygen, the deeper you go into the basin, the more anoxic you get. So that's a situation very similar to the present day Black Sea, for example, where the deeper you go into the basin, the more anoxic you are. It doesn't necessarily mean that the deeper you go, the more the better source rock you have, because there's other parameters that also affect the source rock presence. But in terms of oxygen behavior, you see that very interesting, typical restricted basin behavior. Same thing for the source rock. The deeper you go into the basin, the more anoxic you are. You're not as anoxic here as source rock. You're still at a shallower sea level here, so shallower bathymetry, and the system is slightly different in terms of primary productivity, but you have really good source rock nevertheless. Here we reach our bonus slide for this workflow. So this slide is just to show you that we have the possibility to even take this approach much further by accounting for the sensitivity and uncertainty in the system and really thoroughly assess the risks using our CougarFlow solution, which is our solution for sensitivity, uncertainty, and risk analysis. And there will be a webinar on this topic that will be announced hopefully soon. But what we've done here is that we've selected a bunch of parameters to test their effect on the source rock. And the parameters that we have selected here are parameters that usually directly affect the source rock quality and quantity, and here they are: the primary production, the organic matter, original organic matter quality, the preservation factor, Martin's exponent, and the redox threshold for the burial efficiency. And here you see results from a response surface that was constructed through multi-realizations. And you see results in terms of average and different probabilities of thickness of the source rock, which is anything that has TOC more than 1% and hydrogen index more than 300%. So we set up a really harsh criteria for this source rock. And we see well, on average, we have a very good source rock that's quite thick. It reaches more than 100 meters in those areas. But for even the P90 situation, which is the worst case scenario, we still have in those kitchen areas, we still have about 50 to 60 meters of source rock that has more than 1% TOC and more than 300 hydrogen index. That is, again, just an example of some of the stuff that you can do with DionisosFlow, but there's the possibilities to test for any kind of parameters, input parameters you would like to test for any kind of property of interest that you like to test. Here's an example for source rock analysis, but you could also do the same for reservoir and seal. Now we get to our second Q&A session. So I think we have time for a few questions. Hopefully this time we have a few.
Yes, Samer, we have a few questions. So the first two questions are actually quite complementary. So they are general. I will start with them. The first one is, could you explain what kind of input data, except for wells and seismic, I should have to start sedimentation modeling?
Mm-hmm. Yes. So to start your model, you need an estimation for your accommodation. So that is thickness maps can be an estimation, or if you have some reconstruction of subsidence maps. But also you need your GDE maps to, if you're working with a classic system, to know where to put your sediment sources, or if you're working with a carbonate system, also for knowing where are your carbonate platforms, for example. So you need to assess the volume of sediments that you want to reproduce by accommodation space, and the location of your sediment entry points, or the location of your carbonate systems.
So the second question is actually, so as I said, complementary. So how is the model calibrated? Which data is it possible to use for calibration?
Mm-hmm. The data that you can use for calibration is quite varied. So usually we calibrate to V-shale. You could also calibrate to gamma ray. You could calibrate to sedimentology logs that are that have the different facies. That's in terms of texture, but in terms of thickness, we calibrate to the thickness that is observed at present day. So at the end, the present is the key to the past. So we calibrate to the thickness, but also to the geometries. And there you can calibrate your geometries to present day analogs. If you're, for example, working with submarine fans, that you calibrate the geometry of that fan to present day submarine fans. But also you could use, for example, seismic attributes, such as we've seen the example from Newfoundland, where you have usually very good horizontal resolution of the seismic that can give you the extent of your, for example, turbiditic system laterally, or your carbonate platform, for example, also laterally. And then the Dionisos model will give you a much better vertical resolution that will complement your seismic.
So Samer, quite quickly, because we have actually many questions and you don't have that much time, how to set the flow of sedimentary material into the basin if there are no evident paleo rivers?
If there is no
paleo rivers, no evident paleo rivers, how do we set the sedimentary material if we don't have any evident paleo rivers?
So yes, there is so not always you have the luxury of having the data that you need to construct your model. One way to do it is to try to connect to some global databases that has that information, for example, the NEFTEX Earth model or similar. But you could also try to test end member scenarios. Just put a source where in one location and then completely the opposite. So try to test the end members that might be possible in a certain area if you do not have any information on entry points. So it's by testing scenarios that you could at least try to know something. And for carbonate systems, you could try to use our already built-in suggested values, I would say, and then move around from those and perform uncertainty analysis.
Okay, so to give you some time to rest, 2 minutes, I will answer the next questions myself.
Okay.
So the next question is, are there any restrictions on the size of the model and the size of cells? So actually we work at 2 different scales. We can work either at basin scale or we can work at reservoir scale. If we work at basin scale, in terms of dimension, there is no real restriction, hundreds of kilometers or even thousands of kilometers. Then the limitation will be with the resolution of the cell, which will be kilometric, usually at basin scale, 1 kilometer to 2 kilometers. Sometimes if you are really on a really big basin. And at reservoir scale, the size of the model will be 20, 40, 60 kilometers in lateral dimension. And the cell size will be 200 meters at a minimum, because underneath that, we start having issue with the representation of the transport of sediments through the diffusion laws. In terms of vertical resolution, it's actually more or less the same in the 2 scales. It will be a metric resolution, and as Samer mentioned, it's actually more a temporal resolution with 10,000 to 50,000 years at best in these models. Then we have a question on how many faults can be used in the sedimentology model. So very quickly, because actually faults are not usually a directly input. So you only have to take them into account if they occur at the same time as the sedimentation, which is rarely the case, which can be the case, but honestly, it's rarely the case. Usually they occur after, in a later stage, after everything has been deposited. But if they occur at the same time, if you are in an extensive system, the faults can be taken into account within the subsidence of the basin. And in that case, you can take into account as many as you want. If you are in a compressive system, then it becomes way more difficult if the compression occurs at the same time as the sedimentation. And here you reach kind of a limitation of the software. And for the final question is, are there any relations between accumulation of sedimentary facies and organic matter primary accumulation, or these are separate laws applied in the software? So actually, they are handled separately. So on the one hand, you have the sedimentation that occurs through the river input or through the carbonate production. And on the other side, you have the primary organic production, but then they are coupled within the preservation of the organic matter. So it will more be depending on the sedimentation rates that you will or will not preserve the organic matter. So this is how they are coupled, but in terms of input information, it's a different process. So I think that concludes our second Q&A session. Samer, I don't know if you want to add anything to my answers. If not, I think you can move to the final part of the webinar.
All right, thank you, Alcide. So now we will quickly move into the last part, which is a few slides on the integration of DionisosFlow with reservoir characterization. So here we will talk about what options do you have once you have a reservoir scale Dionisos model. Well, you need to make use of it, and what possibilities do you have to integrate it within your reservoir modeling workflows. But first, let's talk a little bit about the significance. Why would you need to integrate a forward stratigraphic model with your statistical approach or whatever reservoir modeling approach would you have? The reason, the significance of that integration lies in the ability of forward stratigraphic modeling to provide you with a realistic three-dimensional distribution of the sediments and their geometries, and in its ability to qualitatively bridge the gap between the very high vertical resolution but low lateral resolution of core and well data, and the very high lateral horizontal resolution of seismic and low vertical resolution of seismic. So it kind of bridges the gap numerically, process-based, bridging the gap between those two different scales of data. And very importantly, thanks to the integration with our DionisosFlow uncertainty and sensitivity analysis tool, we would be able then to account for the geological uncertainty and transfer that into, or translate that into, the reservoir model. So this is some of the significant aspects of doing that integration. And here we will just briefly tell you a little bit about the options you would have in doing that integration. So option A would be, well, I have a Dionisos model, I have a forward stratigraphic model, reservoir scale, calibrated, I'm happy with it. How do I move forward? One option is to take that model and bring it to present day geometries and burial depth, and use it as your flow for flow modeling, so for reservoir model, or even calibrate it further using some geostatistical algorithms, because as we've shown, if you remember, we've seen that the calibration of forward stratigraphic models is never 100%. It's about 80% or 90% if it's an excellent model. But for geostatistical approaches, the calibration is usually 100% or almost 100%. So you could actually apply a geostatistical algorithm to further match that Dionisos model around those well locations, 200% match your data, and perform the reservoir simulation on that. But another completely different way to integrate or to make use of your Dionisos model in your reservoir modeling workflows is by extracting soft constraints from it for geostatistical analysis. And these soft constraints can come in the form of vertical proportion curves, which usually are generated from well data. But in this case, if you have a Dionisos model, you can generate it from the model, from the stratigraphic model, which does account for the sequence stratigraphic framework and for the lateral variation that the well data would not resolve. You could also have trend maps, you could have facial proportion cubes that you could integrate into geostatistical models, and very importantly, you could generate variograms where you would have a data point in every cell, unlike variograms generated from well data only, where you would only have the well data location. An example of how different your reservoir would look like by using forward stratigraphic model or not. Here you have a map view extraction from one of the units in the model that we've seen in the previous slide. To the left, you have the map to the top left of forward stratigraphic model only, calibrated to about 80% match with the wells. To the bottom left, you have the same model, but calibrated with a TGS algorithm, with a geostatistical algorithm to match 100% the well locations. To the right top, you have the same model, but without any forward stratigraphic modeling, only geostatistics in a TGS algorithm that is matched to the well data alone. While the lower right map is a geostatistical simulation, but with a VPC from the forward stratigraphic model. And here, the take-home message basically is that for the top left, bottom left, and bottom right, even though these look a little bit different, but the flow behavior would be similar, because the yellow is your reservoir, and your reservoir seems to be connected for that unit in those three simulations. While in the geostatistics alone, you would have a very different behavior of your reservoir, because that green is a wax stone, is an impermeable lithology that would change completely your reservoir behavior. So the take-home message here is that when you're incorporating forward stratigraphic modeling results, whether you're taking the model as it is and using it as your reservoir model, or taking some soft constraints from it and using geostatistics with it. You'll have a much better, much more realistic and much more gradual change in your facies rather than abrupt and ungeological changes that you might expect in your reservoir. Finally, just the final message that this we briefly touched is that this integration allows for quantifying the uncertainty, the geological uncertainties. So using cougar-flow and our multi-realization workflow in cougar-flow, we can assess the uncertainties to our model and our forward stratigraphic modeling, and then generate probability of occurrence facies for every facies present out of thousands of results from a response surface, and then use those facies cubes or facies maps, probability maps, to perform reservoir as soft constraints for geostatistical reservoir characterization. And with that, I thank you for your attention, and I think now we can take the last series of questions.
Yes, Samer. So we didn't actually, I think we answered everything during the last Q&A session, so we didn't receive any additional questions. So as I think we reached the 1 hour limit. So I don't know, Olga, if there is anything you want to say before concluding the meeting.
Я думаю, что если у кого-то есть еще какие-либо вопросы, we have the questions.
Yes, we have a final question, which is, could you share the presentation? So I think we can, right? For sure, we can also send you the recording of the video as well. So we will share that with Olga and Katya that was here at the beginning, and I'm sure they can send it to you afterwards because I think they will have your contact information. And can we recommend some literature on sedimentation modeling?
Absolutely, absolutely. We have quite a long list of publications from different environments: carbonates, clastics, turbidite, reservoir scale, and basin scale. So we can provide you with a list of with a collection of those, of course.
So yes, so we will send you all that information afterwards. And could you shortly explain how does the software work, the transition stages of sedimentation, for example, from carbonate sedimentation to clastic or evaporite environments?
Well, again, as we said, those environments can all be active at the same time, and they can affect each other. So if you have your carbonate production parameters in, and you have a clastic source, your carbonate production will be hindered by that clastic source. If you're activating, also we have the ability to model salt deposition, salt precipitation. So if we have also that option active and our salinity in the water reaches above a certain limit, then some carbonates will stop growing, and instead we will precipitate halite or gypsum, or depending on the salinity, depending on the environment, different kind of salts. So they interact together, and they affect the end result of what is being deposited.
So I think that's it. So Olga, maybe you can conclude, and I thank everyone for participating.
Спасибо вам всем большое за участие в нашем вебинаре. Если у вас остались какие-либо вопросы, вы можете без проблем написать нам на почту, позвонить по телефону, мы на всех на них ответим. Как сказал Алсит ранее, мы направим вам ссылку с записью вебинара в течение этой недели. И если вдруг у вас даже после этого останутся какие-то вопросы, вы также можете нам их прислать. Не забывайте, пожалуйста, во вкладочке «Полз», если вам не трудно, ответить на несколько вопросов касательно нашего семинара. Спасибо большое всем за внимание.
Спасибо.